Okay, so hello, good evening, everyone. So, yeah, so how many of you have gone through the first two or three lecture videos of week 5? Like, you can raise your hands. Okay, looks like not many of you have watched it. No issues. So, like, today we will be discussing about the functional dependencies at first, and then we'll be discussing about other topics. Okay, so let me share my screen. Okay, so is my screen visible?
Yes, ma'am.
Okay. So at first, so basically in week 5 and week 6, we'll basically be learning about normalization and how we can design a good database with the help of normalization. So for that purpose, for understanding normalization, learning functional dependency is a very important point. Okay. So today we will try to understand what functional dependency is and also with the help of some examples. So basically, functional dependency, it is like in simple words, it requires the value for a set of attributes to determine uniquely the value of another set of attributes. It could be a set of attributes or it could be an individual attribute. So by definition, in a relational schema R, alpha and beta are the subsets of R, and the FD, the functional dependency, alpha determines beta, holds on R. So to say that alpha functionally determines beta, we say, or we can say, to mention that alpha is functionally dependent on beta, we use this arrow and we mention it as alpha determines beta. So the functional dependency alpha determines beta holds on R if and only if for any legal relations R of R, whenever any two tuples T1 and T2 on R agree on the attributes alpha, they also agree on the attributes beta. So the actual formula is T1 of alpha equals to T2 of alpha, then T1 of beta equals to T2 of beta. So we'll try to understand this particular formula with the help of some examples. So here, if you can see that we are considering A as alpha and B as beta. Okay. So in order to say that alpha determines, or you can say A determines B, we need to this particular condition, both these conditions needs to be satisfied. Okay. So now at first let's check whether two tuples of alpha or two tuples of A are matching or not. So let's consider this as tuple 1, tuple 2, and tuple 3. So we can say that tuple 1 and tuple 2 are the tuples which are matching on A, right? Now what we need to do, if this particular condition satisfies, then we'll head to this particular condition, that is T1 of beta equals to T2 of beta. So basically, if T1 of alpha equals to T2 of alpha, then the corresponding T1 of beta should be equal to T2 of beta. So now that the first condition is satisfied in this particular condition, we need to check for the other condition, that is T1 of beta, or we can say T1 of B equals to T2 of B. So we can see here 4 and 5. So these are not matching, right? So by that we can say that alpha does not determine beta, or A does not determine beta. So now, if we want to check whether B determines A or not, then we can see that okay, all the values in B are unique, right? So when all the values of B or in A are unique, then we can say that yes, beta will determine, or B will determine A. So I hope it is quite clear. We'll try to understand this with the help of some more examples. Yeah. Okay. So yeah.
Ma'am, it's not clear to me.
Yeah. We'll try to understand this with the help of one more example. Let me just try. So again, we are taking A, B, and let us take the tuples as 1, 2, 3, 4, and then say again we are taking 2. Okay. Then we'll take say 1, 1. 3, 3. Okay. So let us consider this is tuple 1, tuple 2, tuple 3, tuple 4, and tuple 5. So now we need to prove that A determines B. Okay. So remember, to achieve this, we need to at first satisfy this particular condition, these conditions. So at first, let's check whether there are two tuples in A which are matching or not. So T1 not matching with other tuples. T2, okay. We can say that T2 and T5 are the tuples which are matching, that is are having the same value, right? So now so this particular condition is being satisfied. Tuple 1 of alpha equals to tuple 2 of alpha. So these so you can say that T2 and T5 are the tuples which are matching or having the same value. Now since this particular condition is satisfied, now we need to check whether the other condition is getting satisfied or not, that is T1 of B equals to T2 of B. So let's check for the corresponding tuples. So T2 of B, we need to check for T2 of B and T5 of B. So T2 of B is 1 and T5 of B is 3. So by that we can so since they are not matching, right? So by that we can say that A determines B does not hold. Why? Because the corresponding because the second condition does not get satisfied, right? If the first condition gets satisfied, the other condition should get satisfied. However, so let's just consider that okay, T2 and T5 is done and it is matching. Now for the other tuples, since all the other tuples are unique, so we can say that okay, A determines B. If like T2 and T5 were matching, only then we could have said that. However, here we can see that T2 and T5 are not having matching values, or the conditions are not getting satisfied, right? So by that we can say that A determines B does not hold. Is it clear? We'll take some
Ma'am,
more examples. Yeah.
ma'am, it is only one pair of tuples or more pair of tuples? Like we are talking T2 and 2 T5, right? So it
Yeah.
makes only
You,
one pair. So
hmm.
what about other tuples like T1, T3, and T4? Do they
So
also need to
yeah.
match?
Look. So T1, T3, and T4. All these three tuples are having unique values, right?
Yes, they are not.
So the
They are not matching
corresponding
with
B
each
value
other.
does not. Yeah, that is why. So if there is a common like tuple, right? As you can see here, T2 and T5. So you only need to check for that those tuples. If the conditions are getting satisfied, then yes, you can say that A determines B.
And
However,
say
if
for
there,
if
yeah,
say for example not a single tuple is matching, then
then we will say that A, like the values, the tuples of A will be unique, or they will have common tuples by the
they will
condition.
not have they will not have common tuple no, when
Okay,
not a single tuple is matching. Like all the
okay,
values are different.
okay,
Say for example T5 is 6, correct? Now
okay,
if
yeah,
T5 is 6, then not a
hmm,
single tuple,
that's
not a
right.
single pair, right?
Yeah,
So
that's
what we
right.
will call? What we will call in that
So,
case?
since all the values of A are unique, so we can simply say that A determines B because all the values are unique, right?
Now,
So,
what
we
is mean
don't
by
need to check any further.
what is meant by this phrase? A determines B means B is dependent on A or what?
That is right. B is dependent on A because we'll at first check check this condition on A, and then only if it is satisfied, then only we will be checking for B, right? So, by that we can say that yes, B is dependent on A.
And if all the values are
Function.
unique, if all the values are unique, then B A does not determines B. A does not determine B, right?
No, if all the values are unique, then we can simply say that yes, A determines B because it does not need to check the criteria, right? If and only if there are two tuples or three tuples or four tuples which are having matching values, only then we will check for this particular condition. If there are no common tuples in the left hand side, then you can simply say that yes, okay, A determines B.
And if say some matching values come, like again T2 is 2, T2 is
Okay,
2, T2 is 2,
and
and
T5.
T5 is also 1. T5 is 1. Sorry, on the right hand side, beta value of T5 is 1.
Beta
Beta
value of
of
T5
T5 is
is
1, 1.
yeah. Hmm.
So now these are matching, right? So now
Yes.
how we will call this?
Now we can say that okay, A determines B because the corresponding values here T2 and T5 are matching, right?
Ma'am,
So we can say
got confused. You are saying when nothing is matching, then also we are calling A determines B. When one pair is matching, then also we are saying A determines B. Then what is the difference?
sorry, can you repeat?
When you just now you said
Hmm.
that when all the values are unique, right? Like
Yeah.
no pair is matching, then we are
Hmm.
calling A determines B, right?
Yes, that's right.
And now on the other side, you are saying when a pair
Hmm.
is matching, then also
Hmm.
we are saying A determines B.
Because this condition is getting satisfied, right? If there are two tuples which are matching, then we will check for this condition. And if this
Okay.
condition is not satisfied, then we will say that A does not determine B. If
Okay.
this condition is getting satisfied, then yes, we, as you said, that instead here we had the value 3, right? So instead you said that okay, here also we have 1. So
Hmm.
now you can see that okay, these conditions are getting satisfied, right? So
Okay. So
by that we can say,
A determines B,
yeah,
and even if all the values are unique, then also we say A
yeah,
determines B, right?
that's right, yeah, yeah.
Okay.
So that is what I'm saying, that at first this particular condition needs to be satisfied. If it is satisfied, then only we'll proceed for the other condition. Is it clear?
Yes, ma'am.
Okay, so we'll take another example. So, okay, yeah. So here we have, instead of just A and B or alpha and beta, we have four attributes, okay? Student ID, semester, lecture, and TA. So we have five tuples. So let us just name it as T1, T2, T3, T4, and T5. Okay. So now let us at first check for student ID, whether student ID determines semester or not. So but for better understanding, let us consider student ID as alpha and semester as beta. So if you remember, our conditions were T1 of alpha should be equals to T2 of alpha. If this particular condition is satisfied, then we need to check for T1 of beta equals to T2 of beta. So now let us check whether in alpha, or we may say student ID, there are any matching tuples or not. So we can see, okay, 1, 2, 3, 4, yeah. So T1 and T4 are having matching tuples. Okay, then another two tuples are also getting matching, are also being matched, right? T4 and T5. So we can say that okay, yes, this particular condition is getting satisfied. Now what we will have to do is, will have to check for T1 and T3 and T4 and T5 whether the corresponding values, beta values, or you can say semester values, are matching or not. So T1 and T3 have same values, and T4 and T5 are also having same values. So we can say that yes, student ID determines semester. Okay. Now, let us check for yeah, student ID and lecture determines TA. So here instead of a single attribute, we are using a set of attributes. So student ID and lecture. So student ID and lecture will be considered as alpha, and we'll consider TA as beta. Okay. So TA is beta. So now let us check whether these conditions are getting satisfied or not. So student ID has some common tuples, if you can recall, and then the lecture attribute also have some common values. However, right now when we find out a set of attributes is dependent on another attribute or not, what we will consider this as a single unit. The student ID and lecture will be considered as a single unit. So we can see that 124 and numerical methods is tuple 1, tuple 2 is 1221 and numerical methods, tuple 3 is 1234 and visual computing. So by that, you can say that all the values are common, all the value, oh sorry, all the values are unique, right? Say for example, if in tuple 3 it was 1234, and in lecture it was numerical methods, then we could have said that okay, tuple 1 and tuple 3 are is satisfying this particular condition. However, here you can see that none of the tuples are like satisfying this particular condition. So by that we can say that student ID and lecture are having unique values, so it will determine TA. Is it clear? I mean, is it making sense? If you are
Yeah,
having,
in the second example, when we take student ID and lecture,
yeah,
so yeah, every tuple. I mean, if you look at it's unique. It appears only once, the combination.
yeah, that's right.
Yeah. So corollary would be like what we learnt in week two.
Hmm.
Any super key. will
Yeah.
always will be functionally dependent on anything else, because super key basically is a subset of the relation
Yeah.
which can be a like a uniquely defines the tuple, right? So by applying that principle and this, I think we can very safely assume that any super key
Hmm.
will be functionally dependent on any other attribute or combination of attribute
Yeah.
within the relation.
That's right. If it's unique, then yeah, we can directly say it.
Yeah,
Yeah.
yeah. I mean, the whole definition of super key is it has to be
Yeah.
unique, right? So that's
Yes,
why.
that's right. Yeah.
Yeah.
Okay. So again, so since in the second option, we were simply taking a single attribute in the right hand side. So let us take set of attributes on both the ends, right? So we will take student ID and lecture again as alpha and TA and semester as beta. So since we know that, okay, student ID and lecture are having unique values, so we can simply say that, okay, this particular condition is also getting satisfied. This particular functional dependency also holds. So
So,
yeah,
ma'am, so
yeah,
here, so since we have proven the second bullet point, like student ID and lecture, defines TA,
yeah,
then right hand side I can make it larger. Any superset of that also will be explained, because that's also a byproduct of the three can be derived from two, basically the third point, because if it defines TA, it can define TA semester as well,
yeah,
or
that's right.
any, right? Yeah.
Yeah,
Okay.
that we will learn. There are some axioms, or you can say there are some rules where this will also be satisfied. So you'll get to know that. But yeah, whatever you said is also right.
Yeah, we don't know. It's just intuitive, right? So yeah,
Yeah,
maybe it will be,
yeah,
yeah.
yeah,
Okay.
that's right. That's absolutely right. Okay, so just for better understanding, we can take one more example. So again, here there are four attributes, and okay, and there are four tuples. So let us take it as T1, T2, T3, and T4. So now let us check whether employee ID determines employee name or not. So let us consider this as alpha and this is beta. Can anybody tell whether it will satisfy or not?
Yeah, because employee is unique.
Yeah.
Yeah, that's right. Since all the values of employee ID are unique, so it will determine any of the attributes that we choose, be it department ID or be it department name. Any of the attributes can be determined by employee ID. So yeah, that's correct. Now let us take the other attribute. This will also be satisfied. Now let us check for department ID and department name. So will this be satisfied?
Yes, ma'am, it will be.
Why? Can you tell? Okay, so
Because
we have
alpha of 1 is equal to alpha beta of human resources.
okay. So
Yeah.
you're
So
saying that
alpha is, if I take T1 of alpha is equal to T2 of alpha as 1 1,
hmm,
even the
yeah,
beta of T1 of beta and T2 of beta would be human resources.
that's right. Yeah. So we can say that yes, department ID determines department name. So yeah. So is anybody having any doubt in functional dependency? Okay. So yeah,
Where we are using this functional dependency.
we will be using these in the normalization forms. 1NF, 2NF, 3NF. You might have heard about it. If not, then we will be discussing this. These.
So intuitively, if we apply it to what we learned in math too,
Okay.
if we take attribute, let's say we are talking about attribute, or let's call it alpha beta, like tuples or unique elements, right? Attributes.
Hmm.
If we create that set on the left hand side and there are set on the right hand side,
Hmm.
if there is a bijective function between these two, then I think this is proven, right? But if there is a many to one, like subjective and all that, then it is not invertible. So I think intuitively looks like if the number of elements on the left and number of elements on the right, there's a one-to-one mapping, the bijective function, then this there's a functional dependency. I don't know. I mean, we're trying to relate to
Hello.
whatever we learned in earlier
Yeah,
semester.
Devasmith.
Yeah.
So you can say exactly it is similar to function. Every time you can see department uh, alpha, department ID is alpha and department name is your beta, suppose. So you can think like the alpha to beta as a f of x, right? And what it will every time if you feed it will output, if input is your 1, then output your what is the f of x value is, that is your human resource, right? So every time you feed 1, it should return human resource, right? Similar for the 2 also. Are you getting my point?
Yeah, yes, sir. Yeah, it makes sense actually. Yeah,
Yeah, yeah.
that's
It
what.
is,
Yeah, yeah.
yeah, it is exactly similar to that one. So it if some non-math student are here, so they are unable to understand it.
I think it was taught. I mean, all functions are relations, but not all relations are functions, right? So we learned that if there's a bijective, then you can say that. So I think now it's
Yeah,
kind
yeah.
of
It
sinking
is
in.
similar to math also. It is whatever see your, you can think department ID is alpha and department ID is beta. So that should returns the human resource, right?
So we lost your audio.
Just a minute. Okay. So f of 1 value is your human resource, right? So every time you feed the f of 1, so that should returns the human resource. Similar to every time you can do that for the other example also. So that is the same thing.
So we call that unique image for each element in the domain,
Yes,
right?
yes, yes,
Yeah.
exactly.
Okay. All right. Thanks.
Thank you.
Okay. So now we will begin with the Armstrong's axioms, or we also specify them as inference rules, so which are used to infer new dependencies, basically to create new dependencies from the existing functional dependencies. So let us begin. So like there are some primary rules, and then there are some additionally derived rules which are basically like implied from, or you can say which generally follow the main or primary rules, and then these are created. So let us at first begin with the primary rules. So the first rule is reflexivity rule, which states that when the right hand side of a particular dependency is of a like when the right hand side is a subset of the left hand side, here if you can see, when beta is a subset of alpha, then we can say that alpha determines beta. So in the form of example, we can say that, say for example, we have sid and lecture, which determines, so say for example we have sid and lecture. Okay. So so okay, yeah, so we have sid and lectures. Okay, so now we can say that okay, there is a reflexivity rule, since a lecture is a subset of sid and lecture, so the reflexivity rule is getting satisfied. Here you can see, so since beta is a subset of alpha, then alpha determines beta. So here you can see that lecture is a subset of sid and lecture, so sid and lecture is determined by lecture, determines lecture basically. Then the another rule is augmentation, which states that if alpha determines beta, then gamma of alpha can also determine gamma of beta. So say for example we have sid determines lecture. Okay, then we can say that semester and sid and semester and lecture will also hold by the augmentation rule. Okay, then the another primary rule is transitivity. So if alpha determines beta and beta determines gamma, then we can say that alpha determines gamma. So by that what I mean is, if sid again determines lecture and lecture determines semester, okay, then we can say that SID determines semester by the transitivity rule. Okay. Now these were the primary rules. So now we'll head to some secondary or derived rules. They generally follow from the main three axioms that we discussed. So they are at first union. So it states that if alpha determines beta holds and alpha determines gamma holds, then by union we can say that alpha determines beta gamma holds. So again, so let's take this example. Sorry, no, we can't take this example. So say SID determines lecture and SID determines semester. Okay, then we can say that SID determines lecture and semester by the union rule. Okay, then we have the decomposition rule, which states that if alpha determines beta gamma holds, then alpha determines beta holds and alpha determines gamma holds. So say let's take this example. So if this particular if say SID is the alpha and lecture and semester is beta gamma, if this holds, then we can say that SID determines lecture and SID determines semester. It is like quite similar to union, but the opposite basically, you can say that. Then we have the last rule, that is pseudo transitivity. So which states that if alpha determines beta holds and gamma beta determines sigma holds, then by pseudo transitivity we can say that alpha gamma determines sigma holds. So basically this would be say SID determines lecture and uh, TA and lecture determines semester, right? Then we can say that TA and SID determines semester. Okay. So by the pseudo transitivity rule. So these were the Armstrong axioms, or you can also say inference rules. These are all the rules that we can follow when we have to find out some new dependency from the existing functional dependency set. So then we'll try to understand the closure of a set of functional dependencies. So by definition, it means that the complete set of all the possible attributes that can be functionally derived from a given functional dependency set. So closure set is basically denoted by if you can see, if we have F, then the closure set of F will be denoted by F plus. So let us try to understand this with the help of some examples. So say for example, we have a relation R which consists of these attributes A, B, C, G, H, and the functional dependency set that is given, that is FD, is A determines H, GC determines B, and CH determines B. Now the question is that we need to find out the closure of AC under these sets of functional dependencies, right? So we need to find out the closure of AC. So remember from the reflexivity rule that if the like attribute is a subset of if the right hand side is a subset of the left hand side, then we can say that like it holds basically, like it satisfies the reflexivity rule. And AC will obviously determine itself, right? A will always determine itself, and C will also determine itself, and AC will also determine itself, obviously. So we get AC. Then we will check. Then we will check what is A or C or AC determining from the functional dependency set. So here, if you can see,
Ma'am,
yeah,
can I interrupt? Is it okay or shall I wait for the last?
yeah. Please go
Ma'am,
ahead.
I haven't gone through the lectures of functional dependencies. I have just seen the first one. So I don't understand what the plus is here, basically.
This is a closure set basically. Like
Okay.
AC, if we want to compute the closure set of AC, by that we mean that the attribute or the set of attribute that is AC, how many attributes or the set of all the possible attributes that it can determine.
Okay. Okay, ma'am. Yeah.
So like which are the attributes that will be determined by AC, all the
Okay.
possible attributes.
Fine, ma'am. Thank
Okay.
you.
Yeah. So now we will check. So now here from the functional dependency, you can see that A determines H. So then we will write ACH. Why? Because A determines H from the functional dependency set. Now we will check whether we are getting other attributes or not. So we have GC. We'll check obviously for the left hand side. So GC is not we have C, but we don't have G in our set, in our attribute set, right? Then we have CH. Okay, yeah. So we have CH which determines B. So we can say ACH and B. Okay, why? Because CH determines B. So then we need to check whether any other, like, are we achieving any other attribute from the AC closure, or is this or are these the only attributes that can be achieved from the closure set of AC? So GC is not present, only C is present, G is not present. A we have taken and CH we have taken. So by that we can say that okay, the closure set of AC is ACHB. Is it clear? We can take more examples also. Yeah. So we have another example where R is the relation and the attributes are A, B, C, G, H, I. Then the functional dependency set is A determines B, A determines C, CG determines H, CG determines I, and B determines H. Now we need to find out the closure of AG. So as I mentioned that AG will always determine itself. So we'll get AG. Then let's check whether A or G is determining any other attribute or not. So yes, you can say that A determines B and A determines C. So we will add A, B, C and G. So because A determines C and A determines G. Then let's check whether any other attribute is getting satisfied. Okay. So we have CG and CG determines H, CG determines I, right? So we get ABCGH and ABCGHI. Why? Because we have these attributes, we have these functional dependencies. So is closure set clear? Yeah.
And one doubt,
Yeah, please go ahead.
ma'am, in this third result, if
Yeah.
CG determines H, then we are considering H also in the result, right? And what the
Yeah.
CG subset of AGBC, how the CGBC came, sir? Ma'am?
So you can see, right, that CG is okay. So this is what it's just the order of like the attributes is different. You can see here it is ABCG. So here CG is an attribute. CG is a subset, right, of AGBC, or you can say ABCG. Here you
Okay.
can see, right, here
Uh,
CG is a
yes,
subset,
CG is
right?
okay. Hmm.
So that is why we are mentioning that CG is a subset.
So this order is
So
not
can we?
this order is
Sorry.
important. This order is important.
No. The
AGBC, or
order
we
is
can write
no. The order is
ABCG.
not important. Yeah.
So we can take the same functional FD set, but
Hmm.
what if we try something like a ACGB,
Yeah.
ABCG?
Yeah.
So let's try ABCG plus.
ACG
It will
plus.
be more
Okay.
interesting. Yeah.
Yeah. Sure. Okay. So please go ahead. You can continue. You can
I think,
volunteer.
well, I mean, applying the principle, it will
Hmm.
define any subset.
Okay.
So it will be A, B, C, G itself,
Yeah.
right?
Yeah.
That's the first one.
Yes.
Then um, all this, I don't know whether we can say AB separately, then CG separately or not.
Yeah.
I
You can
mean,
take that. Yes. You can
okay.
take that.
So AB plus,
No,
CG
that
plus,
is not.
Oh no. That you
no,
can't take. Sorry.
I
No.
can't,
No.
right? Okay.
I
So
thought
it has
that
to
you
be,
wanted to consider.
yeah,
Yeah.
okay, got it. So AB, CG plus, and then
Yeah.
because we have A defines C, so I don't know ACG plus will qualify
Ma'am,
or
can
not,
I
because that's like A B.
Yep. Yeah.
Yeah, go
Fine.
ahead, go ahead.
Yeah, so here it will be ABCGH firstly because CG is determining H,
That's
and
right. Yeah.
then we can have ABCGI because CG is also determining I.
CG.
Also
H.
I ABCGHI. Sorry.
Yeah. That's right. Absolutely right. Yeah.
And there is one more also because B defines H. So if we
Yeah.
replace that, then it will be AC, AC, AB, CG, H also.
We
H
don't
is
need to
already
replace that, right? Yeah, it is
H
already
is already
present.
Already
there.
there.
Yeah, yeah.
Right. Yeah.
Okay, so you said that let's try for ACG plus also. Yeah. Would anybody like to volunteer?
AC, man, can I?
Yeah, sure.
Okay, so first it will be ACG itself,
That's right.
then ACGH,
ACGH because of this functional dependency.
Mm.
Okay.
Then we can have ABCGH because A determines
ABC.
B.
That's right, because of this functional dependency.
Then we can have ABCGHI because CG also
ABCGH.
HI
Okay. Yeah, because of, oh, sorry.
CG.
HI. Yeah, that's right. Okay. So if
Thank you.
we take for AH. Okay. Yeah.
Um,
Yeah, anybody who would like to volunteer?
Ma'am,
Hmm.
is like in the previous one, ACGI is not there, should not be there.
Sorry?
ACG I, like CG also determines I now.
Yeah. So we have it here. ABCGHI. Like you can take it in any order. Say for example, at first we have taken ACGH. Instead of this, you could have also taken ACGI. That would have been completely fine.
Yeah, hello.
Yeah.
Anjana, I think it
Yes.
will be good if we put the bracket and after that the plus symbol.
Okay.
Otherwise, no, no, ACGH in bracket and after
Mm.
that the plus symbol.
Okay.
Otherwise, student will get confused. Yeah. Yeah. Like this.
Ma'am, this plus is for
Closure set.
saying it is a closure set.
Yes, that's right. Okay. So would anybody like to volunteer for AH, closure set of AH?
Well, start at the H. That's the easy one.
AH. Yeah.
Then ABH
ABH because A determines B.
determines
ACH.
Sorry.
CH.
ACH.
A, okay. We have taken ABH, so it will be ABCH, you can say.
Yeah, yeah, that's right. That's
Yeah.
right. Yeah.
Mm. Is it like satisfying any other? Are we getting any other attribute?
No,
No, no.
Yeah,
nothing.
that's right. We won't be getting any other attribute because B determines
Yeah,
H is already like we have both B and H. However, to get these H and I, like to get I, we need CG, right? However, here we don't have G,
yeah.
so we can't get I, or we don't have G
Ma'am,
also.
instead of CG, it would have CH in the F set. Then it would be correct to
Yes,
say that
if it was CH or say CH determines
CH,
I,
mm,
then we could have get AB CH
CHI.
I. Yeah.
Okay.
Okay. So is closure set understood by everybody? Okay. So now
Yeah.
we'll yeah, okay. So now we'll discuss about how we can find out the candidate key or what is a candidate key. So a candidate key is nothing but a set of minimal attributes that can identify each tuple uniquely in the given relation. So remember, every candidate key is a super key, but the reverse is not true. You'll get to know this as we go through some examples. So let us try to understand how we can get the candidate key in a relation with the help of an example. So here we have a relation R and we have the attributes A, B, C, G, H and the functional dependency set, that is A determines H and GC determines A. So now we need to find out the candidate key in this particular relation. So I'll just give you a little trick to find out how the candidate key basically. So what we can do is we have to at first find out all the attributes that are not present in the right hand side. So this is the right hand side of the functional dependency set. So here if you can see that A and H is present, however BCG is not present, right? So what we can do is BCG is not present in the right hand side of any functional dependency, right? So let us at first take the closure of BCG itself. Let's see what we get. So would anybody like to volunteer for getting the
Ma'am,
BCG?
correct.
Yeah, sure.
Um, Ma'am, it will be BCG first itself.
Yeah, that's right. Then
Then ABCG, ma'am.
okay, A, B,
because
C.
GC is
GC determines A.
A.
Yeah. Then
Then we will have CGH. Sorry,
A, B, C, G, H,
CGH.
because A
A
determines
determines H.
H. So we since BCG is determining all the attributes, right? It's determining A, B, C, G, H. The closure set of BCG is basically determining all the attributes, right? So by that we can say that okay, BCG is a candidate key. We can also check for some other attribute sets. So say we want to check for AH. Okay, so let's see. From AH we'll get AH, and then are we getting any other attribute?
No, ma'am.
No, right? So we can't say that AH is a candidate key.
Ma'am,
So okay, say for
one doubt.
example,
How
yeah,
are you getting
yeah.
AH? I mean, how are you deciding that you have to calculate AH?
We can simply take any combination, or you can also
Oh,
take a single attribute. Say we want to get the closure of A, okay?
okay,
Because we need to find out the candidate key, right?
okay.
So say we are taking the like closure of A. So what we will get A
A,
and
then AH.
yeah. Okay.
Yeah.
So are we getting any other attributes?
No,
No, right? So by that we can say that neither A is a candidate key nor AH is a candidate key. We can also try for some other set of attributes. Say we want to try for GC. Okay. So what we will get GC
GC.
itself. Then we will get GCA because GC determines A. And then we will get GCA and H because A determines H. But are we getting all the attributes from the relation?
No,
No,
B is missing.
Yeah, B is missing, right? So we can say that GC is not the candidate key. So from here, okay, let's take BC, the closure of BC. So what we will get? BC.
BC.
Are we getting any other attribute?
No.
No, right? So by that we can say that okay, BC is also not the candidate key. Would you like to try for some other set of attributes?
Any combination, no?
Any combination, yeah.
You can try for GH.
GH, okay. So what we will get from GH?
GH itself and
Yeah,
Nothing else.
nothing
exactly. We
else. Yeah.
won't be getting any other attribute, right? So by that we can say that okay, GH is also not a candidate key because it is not determining all the attributes, right?
Okay.
So any other attributes anybody would like to try? So that is why since none of the other attributes will be like the candidate key or will determine the all the attributes of the relation. So that is why we can use this simple trick like by checking the right hand side of all the functional dependencies. So here we only have two functional dependency sets, right? So what we can do is we can check for the attributes which are not present in the right hand side of any of the functional dependency set. So we can see that A and H are present. However, B, C, G are not present. So that is why we simply took out the closure set of B, C, G, and then we got the
Ma'am, what about the entire attribute set like A B C G H closure?
A, B, C, G, H closure. So that will
Closure.
obviously,
Will that
yeah,
become a super key?
uh, that, yeah, that will be a super key, yeah, because it will,
But the minimality condition is not
yeah,
available.
but it won't be a candidate key.
Candidate key.
Yeah, because candidate key is
Mm-hmm.
basically a set of minimal attributes, right? So, like,
Yeah, yeah.
if a subset of candidate key is also a candidate key, or it is also determining all the attributes, then it won't be a candidate key. So, A, B, C, G, H, you can say it is a super key, but it won't be a candidate key. Okay,
So, ma'am, this trick will help us to get out the candidate
candidate.
keys.
Yeah, that's right.
Like in the right side, if we don't have other than A and H, so we have to take
Mm.
the
Yeah, you can take the
closure.
closure and you can check for much better like understanding. You can also try for some other attributes, some other set of possible combinations, other combinations also, right?
So those combination which will help us to get the entire set
Hmm.
means set of attributes that will be a
Candidate.
candidate key.
That's right. Yeah.
And ma'am, is there any trick
Ma'am, there
to?
is a practice. Ma'am, there is a question in the activities, 5.4 second question.
Okay.
Can we take that?
Yeah, yeah. 5.4, right?
4 second question.
5.4 second question. Yeah. So this is
Uh,
to yeah.
yes, ma'am. So candidate key is B only. And how do we get like super key will be like there are 15. The answer is 15. So it must be 16 minus 1, ma'am. So
Hmm.
how do we get so many combination of super keys?
Okay, so what I'll do is let us at first try to understand how we can find out super keys. Is that okay?
Yeah, ma'am, that is my
Yeah, ma'am.
question. How to
Okay,
get super key for such a function?
super key. Yeah, okay. So that is one next topic. So basically, a super key is nothing but a superset of any candidate key. Remember, a superset of any candidate key. So now,
Candidate key, yeah.
yeah. So let us try to understand this. How we can get a super key with the help of an example. So we have a relation R with these attributes, and these are the functional dependency set. Now we need to prove that AG is a super key. So how we can prove? We have to take the closure of AG, and if we get all the attributes from the closure set of AG, then we can say that okay, AG is a super key. So let's see. Okay, would anybody like to go volunteer? AG closure set of AG.
Can I?
Yeah, it's
Yeah.
Oh,
yeah.
sorry.
Hmm.
Yeah, please continue.
Please go ahead.
No, it's okay. You
Yeah,
continue.
okay. So yeah, it's AG
Hmm.
first.
Yeah.
Then we have ABCG.
Yeah, that's right. ABCG because A determines
A
BC.
determines BC.
Yeah.
Then we have ABCGI.
CGI because B determines I.
Hmm. And then we have ABCGHI
ABCGHI because
because
GC
GC.
determines H. So from the closure set of AG, we are getting all the attributes, right,
Yeah, ma'am.
of the relation. So by that we can say that it is a super key. Now, like,
Ma'am,
how can we identify?
sorry.
Yeah.
Ma'am, you
Mhm.
same you said for the candidate key like.
Candidate key. Yeah, that's right. So, okay, so the difference basically is that if, say, for example, we have ABG, okay, so we can say that the subset of AG is a candidate key, right? Because it will be determining all the attributes. Are you getting my point?
Can you
Okay,
repeat
like,
that?
Yeah.
yeah, so say for example, we have ABCG. We are taking the closure of ABCG. So we have already got the super key, right? AG is a super key, and AG is a subset of ABCG, right? Are you getting my point? AG is
Yeah.
a superset of
Yeah.
ABCG, right?
Okay.
So, so we can say that AG is the super key, or you can say that AG is the candidate key. Now, how we can check is in a super key, the subset will be a candidate key, right? However, if we take the subset of a candidate key, A, say for example, we take the like closure set of A, we will get A, B, C, I. These are not all the attributes from the relation, right? It is not that A is not determining all the attributes. However, if A would have determined all the attributes, then AG wouldn't have been the candidate key, it would have been the super key, because its subset is determining, right, is determining all the attributes. In super key, its subset can determine all the attributes. In candidate key, however, it can't. What I mean by that is, to find out whether it is a candidate key or not, we can use a small tactic, that is, we can check if its subset also determines all the attributes in the relation. If it does, then it is not a candidate key, but a super key. uh, it is not a candidate key, but it is a super key if its subset also determines all the attributes. Are you getting my point? Like, a subset of a candidate key cannot determine all the attributes of the relation. However, a subset of a super key can determine all the attributes of a relation, and that particular subset we can term it as the candidate key.
Candidate key. Yeah.
Yeah, yeah. Is my point clear?
And it
I
could be
Yes,
any
yes.
subset, ma'am. Even if I take out one relation, even then it could be a subset. Eh?
Yeah. Say for example from ABCG. You take simply A, or you simply take B, or you simply take C, or you simply take G. It
Yeah.
will be a subset, right, of A, B, C, G.
Okay.
Yeah.
So if the subset is there, then it is a super key. Otherwise, it becomes a candidate key. That's what you said, right, ma'am?
If the subset determines
Yeah.
all the attributes of the relation, then it
Yeah.
is a candidate key.
Yeah. Otherwise,
And the superset will be a super key. Otherwise, say here, AG, we have specified that AG is a candidate key also, right? AG is
yeah.
also a super key, it is also a candidate key. Why it is a candidate key? Because its subset won't determine all the attributes of the relation, that is A, B, C, G, H.
Okay.
Yeah,
Okay.
so if you can see that the closure of A will give us ABCI, and let's check the closure of G. It will simply give us only G, because if you can see that G is not determining any other attribute. So you can see that, okay, the subset of AG is not determining all the, any of the subset of AG is not determining all the attributes of the relation, right? So we can say that AG is a candidate key. However, we are considering ABCG as super key. Why? Because here we have a candidate key, right? It is a subset of the super key, and it is also determining all the attributes of the relation. So are you getting the difference? Like, is it clear to you?
Yes, ma'am.
Yeah, kind of.
So,
Yeah.
ma'am,
Yes, ma'am.
Ma'am, one
so
doubt I had.
any superset of AG will be a super key, right? So, for example, ACG or AHG.
AHG. Yeah, it will be a super key. Because you can, okay, we can try it out. So, just a minute.
I think with the augmentation axiom, it's proven, right?
By the closure set also you can simply prove it, right?
Right, right.
Yeah. Okay, so what you said, AHG, right? So let's find out the closure of AHG. So AHG will at first determine itself. Yeah, would anybody like to go? Anyone? Two.
ABC,
Yes, ABC,
ABCHG.
HG.
ABCHG, because A determines BC. Okay. Then
EBCG, HGI.
ABCGHI. Why? Because B determines I. So yeah, it's a super key because it is determining all the attributes. And again, its subset, that is AG, is also determining all the attributes. So we can say that AG is also a super key. It is also a candidate key. Is it fine?
And ma'am, I could take out any subset and it should determine, or any one subset is good enough. Like if suppose if I take AH, I'm not sure if it gives me everything, but
Yeah, you can check. Okay, so let's check for AH. So AH will determine itself. Then AH will give A, B, C, and H because A determines BC. Then it will give A, B, C, H, and I because B determines I. Will it give any other attribute?
no, ma'am.
It
That's it.
won't. Yeah. So by that we can say that AH is neither a super key nor a candidate key, right?
Okay, ma'am.
Yeah.
So any one is good enough for having it as a super key, right, ma'am?
One or more than one will also work.
Also be enough. Yeah,
Yeah.
yeah,
So simply what we can do is we can check which attributes are not present on the right hand side. So here you can see that A is not present and G is also not present, right?
yeah.
B, C, H, and I are present. B, C, H, and I are present. Only A and G is not present. You can also check for some other attributes. Maybe they might also give you the super key, right?
Yeah, yes, ma'am.
Yeah.
Thank you, ma'am.
Ma'am, I doubt in activity question 5.3. Could
Okay,
you take
just a minute.
question 6?
5.3, question number 6.
6.
Okay. So here it's given that okay, R is the relational schema and these are the attributes. Then this is the functional dependency set. Now we need to find out which of the options are correct. Okay, so let's try to take this. Okay, just a minute.
Ma'am, after this, please take 5.4.
Yeah, 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 I'll do that. Just a minute. Okay, I'll write it down. GC determines H. Okay, so is my screen visible?
Yes, yes, ma'am.
Okay, so these are the functional dependencies that are given in the question, and we need to find out at first whether AGI is a candidate key or not. So let's check for AGI closure. Okay, so AGI would give us AGI itself, then it will give,
ABCGI,
yeah, that's right.
then
Then
ABCGHI.
ABCGHI, that's right.
That's it.
So all the attributes are getting all the attributes are being determined by AGI, right?
Yeah.
Okay. So we also need to check if any subset is also like determining all the attributes or not. So let us check at first for AG plus. Or you can also check for A, but you know that A will only give A, B, C, I, right? So let's check for AG. So AG will give AG itself. Then it will give A, B, C.
ABCG.
Yeah. Then
ABCGH,
yes,
and finally it will give ABCGHI.
PCGHI. That's right. So by that you can see that AGI is not a candidate key, right? Because AGI is a super key, but it is not a candidate key. Why? Because its subset, that is AG, is also determining all the attributes, right, of the relation.
Okay.
So that is why you can't say. So that is why.
So, ma'am, we have to recheck AGI for
Yes.
its subset. If
Yeah.
if it is determining its subset is determining any
All the
I mean, all the
attributes.
attributes, then we can't say that
It is a
AGI is a
candidate key. Yeah. However, we searched for AG, right? We need to check the other condition is that whether AG is a super key or not. So here you can see that okay, AG is determining all the attributes. So for we also need to check. Okay, so AG since determining all the attributes, so we can say that AG is a
that's a
super key,
super key. Yeah.
right? And AG is also a primary key
How,
because it is determining all the attributes, right, of the relation.
but that is a super key. I mean,
Okay,
AG.
so.
But primary key is also a part of super key.
Yeah, that's right. So, what is a primary key? Can you tell?
Can you please explain?
Okay.
Which is it's a candidate. It's a key that is determined by the database administrator,
Okay. So,
which
what
uniquely determines the tuple.
all
It
the
can be
tuples?
a candidate, yeah. It can be a candidate key. It can be
It
a
can be a
super
super
key,
key. Yeah.
or it can be a exclusive key, which is determined, which is specified by the database administrator.
So basically, primary key, like it could be a super key or it could also be a candidate key. Basically, it needs to satisfy like
Yeah.
all the tuples uniquely.
So what is the
So,
difference between a primary
AG.
key and a candidate key, ma'am?
So if you explain it through a Venn diagram, super key is the superset, candidate key is a subset of that, and a primary key is a subset of candidate key. Like three
Primary key is
concentric
subset of.
circles. Three concentric circles. The outside circle is the set containing all the super keys. Then all super keys, in all, maybe put it this way, all primary keys are candidate keys, and all candidate keys are super keys, but not the other way around.
Yeah, all the candidate keys cannot be a super key. That's right.
Right. Actually,
Is it
sorry,
clear?
ma'am.
Yeah.
Yeah.
What I was suggesting was all primary keys are candidate keys, and all candidate keys are super keys. But the reverse is not true. Like
No,
No,
all
not all
super keys are
candidates
not.
can't be primary. Super key.
Yeah, not all candidate key can be a super key, right?
Just now we saw the example.
Yeah. Every candidate key cannot be a super key.
right, because of closure. Yeah, yeah,
Yeah.
got it, got
Ma'am,
it.
we can say that a primary key can be a super key or a candidate key, but that has to be fixed by the DBA. It has to be selected by the DBA.
Hello.
Hello.
I think the DBA will determine based on the suitability of the key for the domain. We also need to understand the application and the
Yeah,
domain.
but
It's not
it has to be a either a candidate key or a super key.
Yeah. So yeah. So what is the role of DBA here is at first, so suppose we are given a problem statement or case study. So from that we determine what are the applicable functional dependencies are there. Okay. And based on the functional dependency, we calculate which are the candidate key. And suppose there are 2 3 candidate key, and among those candidate key, we fix any one key as a primary key. Okay.
Yeah.
Yeah.
Yes, yes, yes.
And in the
So,
lecture, the example was, there is one, if it is synthetic key or a surrogate key, it can be a primary key, but it's, less useful compared to something more meaningful, right?
Yeah,
So,
synthetic key means suppose if you don't have any attribute that can define the that uniquely identify the any tuple, so we just make one key, say serial number, that is a say key, synthetic key. Okay, that is
right.
simple example. Yeah.
Yeah, yeah. But sometimes the domain also matters, right? So sometimes you could have multiple candidate keys, then you have to pick the one
Hmm.
that makes most sense for that specific application that you're trying to do,
Yeah, yeah.
right?
So
Usage.
it depends on the case study, right? Problem statement. Yeah,
Yeah.
which is more useful. Yeah, that is correct. Yeah. So you can expect such type of problems like combination of this. Like first you have to find out the functional dependencies will given to you. Find out the candidate key, and among those which is the primary key used used for the creation of tables. So
mhm.
such type of
So,
question you can explain. Yeah, expect.
sir, the
Sir, can this
problem which I
5.4 second
said,
be taken?
Yeah, yeah.
5.4
Yes, and then
second
yes,
question.
go ahead.
Yeah,
Yeah.
Priyadarshini
ma'am,
will
my
take it.
question is not done. Please.
Sorry.
So, ma'am,
Yeah,
hello.
yeah, yeah,
Can you get back to the question, ma'am?
yeah. So you got it
So,
right.
ma'am, in this key, AG is a
Yeah,
super key as well as a primary key because we said
yeah.
that
That's
primary
right.
key is a
Hmm.
super key. And ma'am, this A plus
Hmm.
is we can get
Okay.
it
So A plus. Okay. Let's see.
A
Let's
plus.
check for A plus, right? Okay. So A plus, that is the closure of A. So what we will
Hmm.
get? We'll get A itself.
A-
Then
It's a ABC.
A B C. Then
And then maybe CI.
A
C.
B C I. Will we get any other attribute?
Nothing else.
Yeah. So what was the answer? It was A B C I. So yes, this is also a correct answer.
Ma'am, this is an attribute closure set, right?
Yeah. This is
This
an
what we find
attribute
out
closure
is
set.
okay. No, we in the lecture sir said we are discussing functional closure set as well as the attribute closure set. So functional dependency closure set.
Hmm.
Do they both mean different or are they the same?
No, they are the same.
Attribute
Piyush, sir,
closure
correct
set
me if
as
I'm
well
wrong.
as
No, are you talking about the closure of F, like functional dependency?
yeah. In this question we are asked A plus. So this is a
A plus is
attribute
the closure of attribute. Yeah,
Hmm.
closure of
attribute A.
Yeah.
attribute. And
Yeah,
functional
closure of functional
dependency.
dependency means all the possible dependency that can be derived from that functional dependency, say F. So that will be the closure F plus.
Okay.
Yes. So based
So,
on the Armstrong axioms, we can determine like other derived functional dependencies, right? So that
Okay.
comes under the closure of F. Yeah.
That
so in question six,
properties.
so if our question six is modified, if FD is A implies A, which is always the case, then I think if that is the only thing, then both the thing will be the same. Like FD plus as well as A plus are the same.
Sorry, only
If our functional dependency,
hmm?
there is only A implies A. There's no other.
Only A implies A.
Yeah. Is it possible, first of all?
Only one attribute is there in the relation. Like
Yeah,
no, no, no.
it will not be because
Yeah, only
then
one
it's not.
column is there. Yeah, it's not
Yeah,
relation, right?
right, right, right.
Hmm. Hmm.
Okay.
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 So
Thank you, ma'am.
Manan, is your doubt clear?
Yeah, ma'am. Thank you.
Okay. Okay. So we'll move to the question 5.6, 5.4. It was question number 2, right?
Yes, ma'am. 5.42.
Okay. Just a minute. Let me write it down. Okay. So these are the these are the functional dependency set, and we are asked to check. Let m be the number of candidate keys and n be the number of super keys. Okay. So what we will do, we'll at first find out the candidate key. So let's see. So A, C, G, H. We had A, B, C, G, and H as the attributes. So we have A, H, C, G. A. So we don't have B in the right hand side. So let us at first check the closure of B itself. So
B
when we
closure.
check for B, yeah,
B closure, ma'am.
yeah, B closure, then what it will give?
BACGH, it's giving all the attributes.
BA, okay, we'll go one by one. BAH because B determines AH, and then AB determines C, so we'll get BAHC, and then since C determines G, we will get BAH, C, and G. So basically, B is the candidate key of the relation, right? So we have got one candidate key. So what was our question? So we had
M
to let
minus N.
m. Yeah. So the value of m will be 1, right? Now we need to find out super keys. So other than b, there are four attributes, right? So can you tell me if you remember super key, then
Hmm.
any possible combination of candidate key with any other attribute can be a super
Hmm.
key, right? Say
Yeah.
for example, if we take
So, ma'am,
AB.
I'm getting ABC, ABCGH, and ABCH as
Okay.
super keys.
Okay, okay, just a minute. So, what are we getting? AB, we are getting
AB, ABC,
ABC, okay,
ABCG,
ABCG, okay,
ABCH,
ABCH, okay,
CH.
okay. You're getting these four super keys, is it?
Hmm, hmm.
So, can't BC also work?
Yeah,
Or
it can.
BG, or
Yeah.
BH, or
Okay.
say ABCGH?
Ma'am,
Okay.
we
So,
can do the
one formula,
combinations, right? With
yeah,
B.
So
yeah.
these are the
So,
combinations, right?
yeah, so basically what
To
we can
find
do,
super keys.
since there are four attributes, we can take a formula that is 2 to the power 4, which will be 16. Are you getting the point?
Okay.
Yeah.
Okay.
So if you count all the possible combination with the candidate key, we'll basically get it as 16. I've not done all the, if you want me to do, you want me to get all the combinations?
No, ma'am. Like candidate key, we have got one that is B,
Yeah, yeah,
and
that's right.
rest left is four. A,
Yeah,
B, G, and H. Yeah. So, sorry, A, C, G, H,
ACGH,
G,
the
H.
left
So
attribute.
that is yeah, that is 2 to the power 4, ma'am. Super
Yeah,
keys. That is
yeah.
what you are saying.
Yeah, and then the formula that we had to do was n minus m, that is 16 minus 1 equals to 15.
Okay. Okay,
Ma'am,
ma'am.
this is the standard formula through which we can get all the super keys if we are given any relation. I mean, any set like this.
Like there are other formulas also depending on the number of candidate keys and number of if all the candidate keys like if all the attributes are candidate key, then there will be some other formula. So basically we have a
Yeah.
tutorial on super keys and candidate keys. So I
Okay.
recommend you to go through it. This particular doubt will be clear to you
Okay.
all.
Okay.
And also I have shared one link in the chat box. You can see this course link is there. So all the possible how to find out the super keys are given in that post.
Hmm.
Okay.
So that post is enough, like how to find out the number of super key. Just go through it. I will again paste it.
Okay.
Yeah.
Okay.
Okay, so is functional dependency closure set and how to find a super key and candidate key clear to all? Is anybody having any doubt? Yeah. Okay. Okay.
I think it's
Okay. Okay. So yeah, Piyush, over to you.
I think someone is having doubt in week 3 question. Is this here? Amit Kumar is here.
Sir,
Yes, Amit.
so my doubt in week three DBMS questions.
Which question?
Uh, Practice question 2.
Objective or SQL question.
Okay, okay. Can I share the screen, sir?
No. Recording is going on, so you are not allowed. You can check.
Then I
You can tell us the question number. We'll see. Will
okay,
SQL
sir.
question, practice question, or objective
Only
question?
practice question.
Okay, practice assignment question number 3, right?
Yes, sir.
Yeah. Let me share my screen. Subhendu, okay, 1 minute. Subhendu.
Okay, so let me see.
Sir, one doubt. The practice programming assignment questions solution have been in the portal, right?
Uh,
Week 2 and 3, right?
2 and 3, yeah. Is it available, sir?
No. I think we have not released it. We'll release it.
No,
Yeah.
I'm saying the on the portal practice assignment questions.
Practice assignment questions are there, like asking for solution, right?
Yeah.
Those 30 SQL question, right?
No, not that 30. That in the portal itself for week 2 and 3, we have no that practice
Mm-hmm.
graded.
So
Sorry,
you want
practice.
solution for that, right?
Yes.
Okay. We'll see. Okay. Just 1 minute. Let me take this out first. I don't have the question number. Yes, Amit.
Number 2, sir. Question number 2.
Okay. So what? This is a question, right?
No. Big practice question 2. Big 3 practice question 2. 8.
This one.
Yes, yes.
Programming assignment. Okay. So write an SQL statement to find out the element. Okay. So what is your doubt in this? Like,
Sir, I have written the code, but
okay. So you post this QR query on the discourse?
okay, sir.
You can tag me and Subindu. Okay, we'll check.
Okay, sir.
Yeah.
Can I post the selected query on chat, sir? And you can try where I.
Yeah, you can post on chat also, but we have to take a few more concepts so we can see. We can better post on discourse. We'll get back to you.
Sir.
Mhm. Okay. So any doubt in the super key candidate key concept?
No, no, sir. It's just we
Okay.
have to
So let
practice
me
more,
share
right,
my
sir,
screen. Okay.
for getting the
Yeah. Yeah.
super
How
key.
many of you? Yeah, you have to practice that. That's it. So how many of you have watched the tutorials of week 5? There are 4 tutorials are there. Yeah. So we have one tutorial for a super key and one tutorial for a lossless and lossy decomposition, right?
Yes, sir.
So just one thing, let me show. Okay. So suppose whatever we have discussed today, suppose just relation R A B C. Okay. Let us take say student and say we have roll number, we have name, and we have age. Okay. And I am just writing it down here. Say roll number is R01, name is Piyush, age is 25. R02 is say Subendu, say 23. R03 is say Sunita, we have 23. Then again roll number R04 is Sunita, say 25. Again roll number R05 is Piyush, okay, say 27. Now tell me what are the applicable functional dependencies are there. Say this is A, this is B, and this is C. A determine B is there, B determine C is there, A determine C is there.
A determine B
Tell
C.
me.
Oh, sorry. A determine B is there. Okay.
A determine B is there, right?
So B determines C is not there, right?
This determinants is there
No.
because for Piyush we have 25 age, and for same like different Piyush you have age is different, right?
Yeah,
This is not applicable.
correct.
So this one is there. And what is a determinacy here?
Roll number and age.
It is there because age unique, so it is true.
Yeah, it is true. So these two are the applicable functional dependencies, right? So
Yeah.
from roll number I can determine name. So from roll number I can determine age, right? So I can say by Armstrong example, from roll number I can determine name and age, right?
Very
By union rule.
union.
Yeah. Now say suppose I want to update the age of Piyush, and I want to update the age of Piyush. Okay.
Which Piyush?
So how will you identify? Like how will you do? Say suppose I want to update, simply I write a statement, update table name, uh, set age equals to 30, where name is Piyush, right? Where name equals to Piyush. But in this case, what will happen? This name will also get updated to 30, right? This row will also get updated to 30, right? This is with this we don't want, right? Based on the roll number, we want to update the age. So what we can do, like to avoid this anomaly, say this is I'm just taking one example. To avoid this updation anomaly, we are just decomposing this table. So now anyone can tell me how to decompose this table. So we have three attribute A, B, C, say roll number, name, and age. So I can do it either A, B or B, C or A, C or what is BC, right?
This is
Or
done.
BC is done, or say AC or AB. Okay. Now what are the possible combination? These two are right. AB, BC, BC, BC. Now tell me which one be the possible combination for a decomposition out of these three.
ABAC.
AB and AC.
1, 2, and 3. Which one?
One
The
and
third one. The third one, AC.
Third one or first one or second one? Which one?
Third one.
Third one. Okay. So AC. So why third one?
the second is
Because
also AC.
Yeah. So let us discuss one by one now. See, in the first condition, what is happening? If I decompose this as A, B, and B, C, so at first, all the attributes should be covered in both the tables, right? So this is my relation R, and this is say R1, and this is my R2. Okay. So my first condition is R1 union R2 must be equals to R. So means at all the attribute of R1 and R2 must be there in the R, right? So A, B, C is there. So this condition is satisfied in all the three cases. Now, if I say suppose, hello.
Yeah, sorry.
Yeah. Now, say suppose, what is the common attribute here between R1 intersection
B.
R2 B? Now, whether B is determining the my R1 or R2, like from B, like from name, can I get roll number or age? Can I get roll number and age from B?
No.
No. So this decomposition is not valid. Now let us check for second condition. Here also I am getting R1 union R2, right? But what is the intersection of this? That is C attribute here. Now from C, can am I getting the roll number and name? Roll number or name?
No.
No. Now let us take for third condition. That is A, right? So this is A. Now from A, am I getting R1 or R2? Like here you can see functional dependencies, right? So from A, I can get B also. Like from roll number, I am getting name, and from roll number also I'm getting age. So I'm getting both the cases, right? So that is my AC, that is my roll number and age, and this is my roll number and name, right? So what I'm trying to say, we have to decompose this table in such a way that our common attribute must be a key, right? It can be a super key, it can be a candidate key, but it must be a key. So my second condition for the lossless decomposition is my R1 intersection R2 should not be an empty set, right? So there should be a common attribute, and that common attribute should determine R1 or R2. Means And third condition will be R1 intersection R2 should determine R1 or R2. So these are the three conditions for lossless decomposition. So those who have watched the lecture, I think they can correlate this. Hello,
Yes, sir.
are you getting it? What I'm saying?
Yes, sir, it is clear.
Yeah. So we have one tutorial also. You can watch that, or in the next session, I will take one example
Sir, in that
on
you have
also.
in the tutorial you have explained this
Yeah,
lossless
yeah.
join.
So this is for only. Yeah, this is when we want to decompose this relation R into R1 and R2, right? And in the tutorial, I also discussed, suppose we have decomposed this into R1 into R5, and how to check whether our decomposition is lossy or lossless, right? That thing also we have discussed. So please watch that tutorial. Yeah. So any doubt in this part, in week 5 part? Anyone?
We need to do so, then we'll get to know.
Yeah.
Yeah.
So there is one activity question, like whatever we have discussed today. We can discuss that also. Okay, this is a table, and you have to see what are the function dependencies applicable to a given table.
Yes.
And this is the second question also. Yeah.
Yeah. Could you please go through this?
So first one is SID S name. Can you check whether it is holding the table student or not?
Yeah. ID determines name.
Yeah.
SID yes name.
SID S name, right?
Hmm.
Because we don't have like for this roll number we have the same name. Now SID joining date. SID
Sir,
joining.
could you please come back again? Yes,
Yeah.
yes, S001 is having Monty and S001 is again Monty, right? So
Yeah.
both alpha and beta are equal, right?
Yeah.
Yes. So
So
what we are saying that SID determines S name.
S name. That is
Okay.
holding true, right?
Okay. That is
So
our.
suppose, yeah, instead of Monty says a different name is there, in that case then it will not hold true.
Okay. So that's our understanding, right?
Yeah, yeah.
Unlike S02, S002 is also reserve and reserve, right?
Right,
But
Rishabh.
S004 is also reserve. Then what to say in this case?
No, that is fine.
That is fine.
Yeah, like left hand side is uniquely determine the right hand side, right? It is,
Okay.
yeah.
So
Here, yeah.
SID is just name, right?
Hmm.
And say for example, if the second S002 could have been other name like Neha or something else,
Then in
then
that case it will not hold. Yeah.
okay, then but whether still we will say that SID determines S name, then we
No, no,
still
no. Will not say.
but one is there, na? Yes, not one. S001
No,
Monty
for all the tuple it should satisfy.
for all the tuples it should satisfy. Okay.
Yeah.
So I think in this case, if we replace that S004 is Rishabh, if
Hmm.
it is something else other than Monty or Rishabh or Neha,
Hmm.
then S name can determine SID.
Yeah.
Other way
So
around.
yeah, in this, if we replace this and this Monty, right? Yeah, this Rishabh
No,
also.
no, no, only that
Only,
S004
yeah,
because
this one.
only
Yeah, right.
with something which is not Monty, Rishabh or Neha, then S name
Yes,
would
yes.
determine. Yeah,
Then reverse is true. Yeah.
yeah.
So now second one is SID determine joining date. So all the joining dates are same.
I think
So
yes. I think yes.
yeah. So this is also true. Now hostel ID determining room ID. You can check.
It is not, sir, because H3 has two different values.
H3 has two different, right. So this is not true. So first and second is the correct one. Now this is a good question. Say suppose if hostel ID determines S department, right? Say hostel ID determines S department, then what is the value of ABC? What is the possible values of? Okay. Just tell me what is the possible values of A, B, C then if hostel ID determined as department is true.
So then A has to be CSE.
S3 A, yes, A is CSC, A is CSC.
B can be anything, no
B
restriction.
can be anything.
Even
And
S4 can be
H4
anything,
is
C can be anything,
anything. Yeah.
But
C can
A
also
must be,
CSE, CSE.
yeah, A should be CSC. That is correct. And what are the correct option? Okay, we can check this again. Okay, so please solve all the activity question. Okay, it is easier. Like whatever we have discussed today, you should be able to solve this. And we have few tutorials also. Okay, any doubt in this week 5? Anyone? There is one important tutorial on dependency preservation. You can watch to it because this week 5 is like say prerequisite for week 6. If you didn't understand the week 5 content, you will not get the week 6 part because in the week 6 we'll be starting with from week 5 only. So it is application of week 5, week 6 basically.
So for the quiz one that is coming up, is it week 1 to 5 or week 1 to
Week
4?
1 to 4 only. Yeah.
Or 4 only. Okay.
Yeah, so anyone any doubt? I think in division we have 5 columns in A. We divide by B. Just 2 column canvas plus division will work out. Okay, any doubt? Still we have half an hour left. We can discuss anything. Okay.
Sir,
Subhendri,
if yeah,
yes,
sir,
yes.
if time permits towards the end of the session, could you please explain the concept of natural join very quickly
Okay. At
towards
first, Amit Kumar is
towards
here.
the end?
Amit Kumar. Yeah, Amit. Okay. Amit Kumar is not here. Natural joint concept, right?
Right, sir. Right.
Okay. Okay. So suppose we have two table. Say R1. We have column A, B, C, and we have say A1, A2, A3, B1, B2, B3, C1, C2, C3, right? And we have R2. We have there are two cases. Okay, so at first say C, D, E. So C1, C3, C4, D1, D2, D1, E1, E2, E3. Okay, now R3 is say B, C, and D. Okay, now here B1, C1, B2, C3,
So these
and
BCD are common attributes, right?
no, these three are complete different relation. I am coming to that. Just 1 minute. D1, D2, D3. Okay, so my screen is visible, right?
Yes, sir.
So this is my R1, this
Yes,
is
sir.
my R2, this is my R3. So first thing is that we'll perform natural join between R1 and R2. Okay. Now what is natural join? So based on the common attribute, it will match the common tuples. So what is the common attribute here? C, right? Hello.
Yes, sir.
Yeah. So C is the common attribute here. Now based on this attribute, it will match the common tuple. So for example, C1 is here, so C1 is also is check for C1. So C1 is matching with this. So the output will be A, B, C, D, and E. So here I will get A1, B1, C1, D1, E1. Now any other C1 is there? No. Now
No.
let's check for C2. C2 is not matching with any of the tuple in the R2, right? It's C column, so C2 will not come. Now check for C3. Yes, C3 is there. So output will be A3, B3, C3, then D2, then A2, right? So this is the output of R1 R1 natural join R2. Because one, if we are having the common attribute, right? Hello, Ganga Prasad is here.
Yes, sir. I am listening to you, sir. Yes.
Okay. Now second case is that R1 natural join R3, right? Now here B and C is common attribute, right?
Yes, sir.
Now based on the common values, it will match the particular tuple. So here, if you perform the R1 natural join R3, so what is B1 C1 is there? So you have to check the combination of B and C, okay? Not individually, B and C. So B1 C1 is here. Yes, B1 C1 is here. So output will be A, B, C, D, and here say A1, B1, C1, and it is D1. Now B1 C1 is there? No. So B2 C2 is there? B2 C2 is also not there. B3 C3 is there? So B3 C3 is also not there. So this is my output. So this is case second, like R1 intersection R3 when there are two attributes are common. Now third one is that when there are no attributes, say R4 is RDE, and I am performing R1 natural join R4. So in that case, what will happen? It will perform the Cartesian product, Cartesian join. Okay. Hello.
Yeah.
Yeah.
Yes, sir.
So what is your
You
okay?
know,
So any
so
doubt in natural
you're
join
saying
part?
that when tuples are not common, then it will only take Cartesian join, right? Otherwise, it will take common
Yeah.
value.
Yeah. Common. No. See. Common attribute I'm talking about. So R4 is my D and
Right,
E.
right.
In that case, it will perform Cartesian join.
Yes.
Now, say suppose this is here instead of B1, I will make it as B2. Okay.
Hmm.
Now just see R1 natural join R3. Now B1 C1 is not there. B2 C2 is not there. B3 C3 is also not there. Now in this case, it will return empty table, right? It will not fetch any particular tuple, just read empty table will be there. It will
Hmm.
not perform the Cartesian product because common attribute is there. But common attribute is not there, then it will perform the
Okay. And sir,
Cartesian
I'm
join.
also, I'm not so clear with one more terminology.
Uh, Sorry, you are not
Hello, sir,
audible.
am I audible?
Yes.
Now am I audible, sir?
Yes, you are audible. Yeah.
I'm also not clear about one more term, sir. Like there are two types of join, right? Inner join and outer join, right?
Hmm.
So whether the word natural join can be associated with any kind of join or natural join itself is a altogether different join.
No, natural join. What internal it will do based on the common attribute, it will match. It will perform the join operation. Now, what is inner join is that
No,
okay?
I am saying that whether the word natural join can be
Huh.
associated with any kind of join, like left join, left natural join, right natural join. Can be right like this, or natural join itself is a
No.
complete different types of join, different type of join.
It's a complete different type of join, I guess. But left joint is also there, right?
Yes, and we call left natural join, right natural join, and then
Ok- Left outer joint, right outer joint. Yes, you can try it out. In some database system, it will allow, but I am not sure about it. You can try it out. Left out,
okay.
left natural joint. You're talking, right?
Yes, yes. Even professor has used this word, left natural
Okay,
join,
okay.
right natural join. So now this brings a confusion that whether natural join is altogether different join or it can be clubbed with anything.
No, we can do. I guess you can check in the PG admin. You
Yes,
can try
sir.
it out. Yeah.
Okay.
Yeah, hello, Ganga Prasad.
Yes, sir. Yes, yes.
Hello. See, natural join you understand.
Hmm. Yes.
So left natural join like the same thing, and the left whatever the left table will be there. All the attributes will be there, and the natural join will be there. It, professor will explain in very detail. You can watch the session. The
Hmm.
similar thing, right? Natural join.
And then full natural join.
Yeah, full natural join.
So okay, so what we are saying that natural join itself is a separate join, and at the same time it can be clubbed with any kind of join. That's what you
Yeah,
are
yeah.
trying to say.
Yeah. So let me share my screen. Okay. So, okay.
Okay, okay.
Okay. So you understood, or hello, Ganga Prasad?
Yes, I will go through it again,
Yeah,
and
yeah.
then if required, I will ask on
Yeah,
Saturday.
or you
I will
can
ask
post
on Saturday.
also on discourse, and you can tag me.
I'm not so active on Discourse, it takes a lot of time.
Oh,
Okay, I will ask on Saturday.
okay, okay.
Yeah, you can also try and PG admin. Like for Postgres, I don't know whether it will work or not. But yeah, in MySQL it is working. So yeah, you can check it also. Okay, so this thing is clear. Okay, any other doubt in week 5? So next week we'll be having one session for a quiz one, like revision session. So if you please watch the week 1 to 4 content, and also we'll be releasing the mock test on Tuesday. Quiz one mock test.
Sir, after revision, release it, sir. First of all, revise the concept, then release the mock test.
Yeah, so that mock will be open for till the quiz one. Okay, so you can give it
Okay.
anytime.
Okay.
Hotel quiz one mock will
And
be
keep a
there,
longer
right?
duration for revision, sir. Please keep a longer duration, sir. Because we need to cover all the 4 weeks, right?
Yeah, yeah. We can extend till 3 hours. Okay, no issue. Yeah.
Yes. Sir, graded assignment question number 6, sir, of week 4. Could you please explain? It will not take much
Uh,
time, hardly.
yeah,
Question
okay.
number 6,
Subindu.
graded.
Yeah.
Question number 6, graded assignment week 4.
Okay, okay. Yeah, sure.
Okay. Let me share my screen. Which question?
Question
Question
6.
number 6. Question number 6. Yes.
Okay.
Yes, this one. This one. Yes, this
Okay.
one.
Okay.
See, as per my understanding, there are three relations: doctor, patient, and then operation roster. Right? These are three relations, right?
Yes.
And then
So
patient is having. Yeah. Please carry on. Yes.
see, doctor having doctor ID, doctor name, and specialization. The patient number, and the patient name. The operation roster, doctor ID, and the patient name is the combination of the candidate key, right? There, make this is the composite key and the operation code.
Right.
Identify the appropriate expression to find all the distinction about the patient operated either by Dr. Nath or by Dr.
Joseph.
Joseph, right?
Yes.
So you can see that. Uh,
Yes, I can see it. Yes.
so if you say the patient and the natural join patient number, sorry, natural, so it's not see right. So yeah, we have to find the approved distinct name of the patient, right? So patient name, okay.
Right.
In that, uh, we have to who operated either by Dr. Nath or by Dr. Joseph. So
Okay.
doctor
So
name equal to doctor.
let us read first option. We are
Yeah,
projecting patient name, right? We are projecting patient name, right?
yeah.
And
From the patient.
we are joining patient join
Patient
patient
name.
number.
Yeah.
But but
And the
but no here my confusion is coming. The patient is a table, right?
yeah,
Patient is a relation, right? And
yeah.
patient number
Patient is
is an attribute. Patient number is an attribute. Then how we are joining a table with an attribute? Because we carry out
so
joining with two tables, no, with respect to two
so
tables, right?
okay.
That is
See
my doubt.
what okay. See what will written patient projection of patient
Hello,
numbers.
sir, you are
Yeah,
not
am I
audible, sir.
hello?
No, it's breaking. Your voice is breaking, sir.
We
Anyone
can
can
hear.
Is it
We can hear clearly. No problem.
yeah now my voice is audible.
hello?
Yes, sir. Yes, sir. You are very much
Yes, sir.
audible.
Yes.
Okay,
Yes,
see,
sir. Yes. Yes.
you have to find the distinct names of the patient operated either by Dr. Nath or by Dr. Joseph, right? So you can see that you have to find the doctor
Hello.
name by Dr. Nath or Dr. Joseph. So you can see that whatever the patient number we will get from that, right? Hello.
Whenever we are, my doubt is that whenever we are carrying out a joining operation, it
Yeah.
is between two relations, right? It
So
is between two relations.
so so it will give the projection of patient number, right? So patient
Right.
numbers. So see, you can see that patient, whatever the patient is there,
Yes.
and a
Yes.
natural joint projection of whatever we get patient number. Suppose there are okay. So
Oh,
let's me okay 1 minute. My screen is visible. Hello.
yes, sir. Your screen is visible.
Okay. So whatever the attribute is there, if you see the patient number and patient name. So patient patient number and the name, right? Hello. Suppose one patient number is Ram, two patient number is Raj, three patient number is Rakesh. So whatever the projection of patient number, this is patient. What we get?
One, two,
Patient
three.
number 1 to 3.
Yeah.
So then we can natural join, right? So we get projection. After that we will get projection. Then we can join. We can do natural join. So Ganga Prasad, it is clear.
Okay, sir. So you are saying even a table can be joined with an attribute.
Yeah. So first we projection or projection we get a
Projection is outside the
relation, right?
bracket, na?
Yeah. So see, we get after the projection we get.
See,
So see percent. Then whatever the projection we get after to do natural join.
sir, let us read the first line. How to read it? Projection of patient name, right?
Yeah.
And projection of patient name is coming from patient inner
Natural
patient
join.
out natural join patient number, right? Projection of
Yeah.
patient number.
Yeah. From
So
that.
patient is a table, right?
Yeah. Percent is a table.
And that is getting joined with patient number.
Yeah, patient number. See, patient number with a given condition. Doctor name equal to Doctor Nath and the Doctor Joseph and Doctor Natural Join operation. Whatever the we get Doctor Natural Join.
Okay. Okay. So we are carrying out joining here, doctor
Yeah,
and operation roster.
yeah.
Okay. Okay.
So yeah. So
Okay.
you got it.
Yes. 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 Okay.
Yeah, so Ganga Prasad, we can join table with the attribute also. Say for example, the example we discussed just earlier. Say
Yes.
instead of R1 in natural join R2, I can simply do R1 natural join projection of B R2. So it will match with the common rows from the B attribute
I
like
got
that.
it, sir. I got
Yeah.
it because the projection is happening after one more joining, right?
Yes.
That link was missing from my side. I got it, sir.
Okay. Okay.
Thank you.
Okay.
Thank you.
Okay. So yeah, Amit Kumar is here. Okay. If you have any doubt, you can ask, or we can close the session.
So I'm
Yes, sir.
having a doubt in division operation. Can I ask?
Yes.
Okay, in the lecture it is given with three columns. Okay, instead of that, suppose R is having four columns.
say A, B, C, D, and S is
Ah,
having two columns, say C and D. So I have to always check the combination of C and D with R, right? If R divided by S.
yeah, yeah. So you have
So
to.
in yeah, please go
So,
ahead.
yeah, let me give one example. So you are talking about, suppose there is A, B, C, D,
Yeah,
any your combination, right? So
right.
suppose what you have to check, right? A, B, C, D, A,
Hmm.
and you have to suppose divided D and E, right?
Right.
Okay. So suppose there are D is
Yeah,
D1, E1, and D1. Suppose E2, right?
right.
Okay. So suppose A1, B1, and okay, 1 minute.
So my query is something else. I know that I have to check the combination. Like for
Yeah,
example, D1, even both the things D1 and E1 is present in a particular tuple.
yeah,
My
yeah,
query is if suppose there are two records,
yeah,
say
yeah,
A1 B1 C1
yeah,
D1 E1
yeah.
and A1 B1 C2 D1 E1. So
Oh,
will those both the tuples will get selected or the values should like
okay,
I mean
okay.
I'm a bit confused with
Okay,
that
can
thing.
okay, please, A1, B1, then
C1
okay, C1,
and then D1 E1
D1,
E1.
E1,
And
then
over here again A1 B1 C2
A1,
B1
B1, C2,
C2
then
D1 and E1
D1 and
E1.
okay, yeah,
So the first three columns doesn't matter, right? Any value, even if they are matching or not, they will get selected.
yeah. So you have to check this, this whatever the D and E present is, A, B, C corresponding is there or not.
Okay, okay. So in this case, both the records will get selected.
Uh, but
No, D1, oh, D1,
D1 it
E1
is
and
not there, right?
oh, so nothing will get selected
Yeah, yeah,
actually.
nothing. So there is a one tutorial on division operation you can watch also, and in
Right.
the one live
Okay, I got it.
session we also discuss division operation, how it works. So you can,
Okay, okay.
yeah,
So actually, in is it like that in such cases, there should be only one record, na, sir, in that case, in S, because if there are multiple records with multiple combination of the columns, nothing will get selected because at any particular point of time, D1 and D2 cannot be there in a
yeah,
particular
it
tuple,
can be,
right?
you have to check all the combination. If it is there, it can be, you have to check all the, suppose there is a, let me simple example, suppose there is A and B, and suppose there is a
Okay.
B. So B is there, suppose 1 2.
Yeah.
So suppose there one is 1, then one also is 2, then suppose 2 is
Okay.
also 1, then there will be selecting one, right? If A there is R and this is S, so R divide S will be 1 because 1 and 2 is both present in 1, right?
Oh, I see. Okay, 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 okay.
So you
So
have to check,
basically, okay, okay, I understood
all
now.
the combinations. So
So
you
in
can,
this case, suppose there is one more record A2, B2, C2 and D1 and E2, then that particular thing will get selected.
yeah,
So
yeah,
basically, ABC values should match,
yeah,
right?
yeah,
The combination.
yeah, yeah.
Okay, okay. Oh my God, doubt got clear. Okay, thank you, sir.
Okay, and any other doubt? Okay, then we can wind up the session. Thank you everyone.
Thank you very much, sir.
Thank you.
Thank you, sir.
Okay, thank you, sir. Thank you.